ગુડ આફ્ટરનૂન ઓલ. જાની સાહેબ, અવાજ સંભળાય છે?
હા સાહેબ, સંભળાય છે. હા હા.
ઓકે. થોડીક લિંકની ગડબડ થઈ ગઈ હતી, એના લીધે ઇવેન્ટ પૂરો થયેલા ઇવેન્ટમાં આપણે બધા હાજર થઈ ગયા હતા. હવે એ ચેન્જ થઈ ગયું છે ધીરે ધીરે. બધા પાર્ટિસિપેટ આવી રહ્યા છે. ઓલરેડી 23, 25 ઉપર વયો ગયો છે આંકડો. આપણે 5 મિનિટ રાહ જોઈએ છીએ ભાઈઓ બહેનો. Then we start our second session of electrodynamics. Dr. K. Jani delivered the lecture. You are wait for the 5 to 6 minutes because I just sent the link to everybody. So it will take 3 to 4 minutes to join each and everyone. So we wait for a 5 minute. Thank you for listening. જાની સાહેબ, ત્યાં સુધી આપ તમારું શરૂ કરવાનું તમારું પીપીટી છે એ પ્રેઝન્ટ કરવા ટ્રાય કરી લ્યો. બરાબર? આપનું માઇક બંધ છે જાની સાહેબ.
હા સાહેબ.
હા, આપનું પીપીટી તૈયાર, પીપીટી ગોઠવી લ્યો એટલે પછી આપણે એ સમય ન બગડે.
દેખાય છે સાહેબ સ્ક્રીન? આવી જાય છે ને સાહેબ?
યસ. તમારું પીપીટી શરૂ કરજો સાહેબ. શેર કરજો.
સ્ક્રીન ઉપર નથી દેખાતું સાહેબ?
ના, સ્ક્રીન ઉપર નથી આવ્યું હજી. હવે
મેં કરી દીધું અહીંયા ચાલુ.
બેટું
મેં કરી દીધું છે સાહેબ ચાલુ. સ્ક્રીન ઉપર નથી દેખાતું? મારા સ્ક્રીન ઉપર આવી જાય છે. હેલો.
હા જાની સાહેબ.
Yes, sir. Hello.
હા સાહેબ join થયા છો?
હા હું સાહેબ જોઈન જ છું હો. તમારું માઇક મ્યુટ લાગે છે.
હા જાની સાહેબ હવે આપણે શરૂ
હા હા
કરીએ
સર.
સાહેબ. ઓકે
ઓકે ઓકે ઓકે સર.
ઓકે સાહેબ આપ તમારું પીપીટી શેર કરીને શરૂ કરી દો છો. હું શેરિંગ સ્ટોપ કરું છું. આપ આપનું પીપીટી શેર કરીને શરૂ કરી દો.
Okay, sir. Okay. Good afternoon, everybody. સંભળાય છે સાહેબ? મને લાગે છે પીપીટી દેખાય છે.
હા સાહેબ અવાજ આવે છે.
પીપીટી ચાલુ થઈ ગયું ને સાહેબ? હેલો.
હેલો.
I think slide is visible. સ્લાઇડ વિઝિબલ છે ને સાહેબ? જસ્ટ હેલો.
વિદ્યાર્થી ભાઈ બહેનો આપને સ્લાઇડ દેખાય છે? ના સાહેબ સ્લાઇડ આપની શેર નથી થઈ.
મારે અહીંયા બતાવે છે એટલે
તો વિદ્યાર્થીઓ તમને દેખાય છે? કોઈ
પ્રેઝન્ટર તરીકે મને મૂક્યો છે કે જરાક ચેક કરો તો.
પ્રેઝન્ટર તરીકે જ છો સાહેબ આપ. આ પ્રેઝન્ટર તરીકે જ છો.
મારા
આપની
કોમ્પ્યુટરમાં
સ્લાઇડ
બતાવે.
ડેસ્કટોપ
મારા
ઓકે
કોમ્પ્યુટરમાં બતાવે છે.
હા હા સાહેબ તમે શરૂ કરી શકો છો. દેખાય છે.
ઓકે ઓકે ફાઇન.
Okay.
Okay, so good afternoon, everybody. And in this second session of this lecture series, I welcome you all. There was some technical problems, so we have to start this session little later. And we shall continue in this session with the problem that we have started in the last session. Let me give you a small recap, and if you have any doubt in these 2 days, you can ask me right now. We started with the problem of electric dipole. First, we understood what is the radiation. Our first point was what is radiation, and then we went to the problem of the electric dipole. So in radiation, we show that if we have electrostatic field or magnetostatic field, in this both cases, the energy stored in the fields are shown by this equation. But if it is electrodynamic field, if it is a field produced by the charges in motion, then we have the energy stored in this electrodynamic field represented by the equations shown in the bottom of the slide, where we have seen that the second term represents the energy which is escaped from the given volume from the electrodynamic field, and we said that this escaping energy or leaking energy can be of the form of a radiation if it uh, follows certain conditions. What were these conditions? So we said that if the energy which is leaking out, okay, the field lines of this flux of energy, if it follows 1 upon r square dependence, that is, if we take the flux from the source of the given electrodynamic field. Now, out of the volume that we have considered, if we measure the flux and if it follows 1 upon r square dependence, if we go on taking large and large volume, uh, having large and large radius, then if the flux coming out follows 1 upon r square dependence, then it tells that this flux or the leaking energy can reach up to the infinite distance, because the total flux coming out of the sphere, the total flux remains always constant in this case if it follows 1 upon r square dependence. So we can take a sphere or the volume of infinite radius and still it can have the flux associated with it, the constant flux. So we say that radiation or the energy is leaked or escaped in the form of radiation. But if it followed 1 upon r cube or 1 upon r raised to 4 dependence, then the case would have been different, and in that case some of the flux lines would terminate in between, and at infinite distance, if we take the sphere having infinite radius, then no flux would be associated with the surface of that particular sphere. So this, if it followed 1 upon r raised to 3 or r raised to 4 dependence, then we cannot expect the energy to flow to the infinite distance in the manner that it is irreversible. We cannot have the reversible flow, irreversible flow of the energy. So then we said that since in the electrodynamic field we have the term, suppose you take the case of electrostatic and magnetostatic, the energy stored or the work done by the field is given by E square or B square. In both these cases, if we take Coulomb law into consideration or the Biot-Savart law into the consideration, which can cause electrostatic or magnetostatic field, then we get 1 upon r raised to 4 dependence. And because of that only, we say that the electrostatic or the magnetostatic fields do not leak energy in the form of radiation. So this is one case. But here in the case of electrodynamic radiation also, we have the Poynting term which shows the leaking of energy, but in that also we have a Poynting vector in the form of 1 upon mu 0 E cross B. Now if you again take E and B in the form what we used to take in electrostatic and magnetostatic, that is Coulombian representation and the Biot-Savart law representation, then again E cross B would have 1 upon r raised to 4 dependence. So in that case also we cannot expect the energy, leaking energy. There is an energy which is coming out of a definite volume, but if we put it to the limit of infinite radius volume, then you cannot expect this Poynting vector to give energy flow. So we cannot expect radiation. Still we get radiation. So let us inspect the what form it has. Okay. Obviously or apparently E cross B cannot radiate the energy in the form of radiation. But so what would have happened? So we then after have seen that we cannot take E and B in the same footings that we used to take in the case of electrostatic and magnetostatics. So then I showed one slide in which I said that suppose if we take the Coulombian form which says that as soon as there is a charge, there is a field around the charge instantaneously. So if you allow the charge to change its polarity frequently, then as soon as it changes its polarity, there is a change in the field instantaneously. And we said that this approach is not valid in the case of electrostatic, because we cannot expect field to spread in the space with infinite velocity. Okay, so the the maximum value of the velocity with which it can spread inside the space is the speed of light. So this is not the situation. So we have to take that form, which takes some definite time to spread into the space. That nature of field we have to take into consideration, and we did that, and we said that we can expect this type of situation in which as soon as the charge changes the polarity, uh, this field, this information starts spreading in the space, and it transfers, or it propagates with definite velocity, that is the speed of light. So we have the situation something like surface waves in the surface of water, where when you put the pebble on the surface of water and you get this type of waves. Okay, so this type of changes in the electric field you would expect. Okay, so let us take an example of this oscillating dipole, and let us see how it is emerging, this type of waves or time varying electric field in the case of dipole oscillation, the field which is caused by the dipole oscillations. Okay, so we went on to derive the field of electric dipole. Okay, charge which is oscillating, dipole, electric dipole which is oscillating with definite frequency omega. Okay, and then we went to see what is the electric and magnetic field caused by this oscillating charge. Okay, so we intended to actually work out what is the form of the electric field and magnetic, of course, magnetic field, and how is it different than the field that we represent with the Coulombian formula or even the Biot-Savart law, how they are different. So to inspect the nature of electric and magnetic field, we took this example. So then we took this dipole which oscillates with, I think, are you able to, okay, now it has come. Okay, so then we took this oscillating dipole. In this dipole, the two charges continually continuously changing its polarity. Both of them, they change their polarity with time, and we expect the electric field caused by this varying charge value of these two charges, and to derive this electric field, we first derive the potential, electric potential, time varying electric potential. Then we consider the current which is caused by this oscillating charge, and from that we can find the time varying magnetic potential. So our first task is to find both type of potentials, which are the component of the electrodynamic field. So how to derive the potential, electric time varying electric potential? So we said that both this uh, charge can be shown by changing sinusoidally. the value of the charge, and the upper end charge we are representing with Q plus, the lower end charge, the change in the lower end charge, polarity change in the lower end charge, we represent with Q minus, and then we say that if we take a point some r distance apart from the center of this dipole, okay, and how to measure the time varying electric potential. So we say that the instantaneous position of both the charge, or instantaneous value of both the charges, are not measured at point P, but the value which is measured at point P, where the value of the charge is sometime back. So that is, it measures the retarded potential. So we have to take into the consideration, and that we showed with these equations. Okay, how to measure? So okay, retarded potential due to the upper end charge fluctuation is shown by V plus, lower end charge fluctuation is shown by V minus, and both would be different because distances they have to cover are different. R plus and R minus are the different distances that they have to cover, and we have to put at the place of T the retarded time. Okay, so then after we went on to derive the value of R plus and R minus. I'm not going into it once again, but these things we have derived the value of R plus R minus, and then we took our first approximation. We take here three approximations actually, and the first approximation was that this R is very much greater than D, where D is the maximum separation between the two charges, oscillating charges. So it is of the atomic order of the order of 1 angstrom, where R is of the order of centimeter or meter. So R is much greater than D. We took that for approximation, first approximation, and from that we actually found out the value of R plus and R minus by employing binomial expansion. After getting the value of R plus and R minus, we took the potentials at point P, which are caused by both upper end charge and lower end charge. We took the summation of these two, basic summation of these two, and in that equation, which is shown in the bottom of this slide, in that equation we have put the value of R plus, R minus, 1 upon R plus, 1 upon R minus, and then we expanded the whole term. I am not going into the mathematics of this expansion once again, but then after we reached to the result in the last slide, which is shown here. Okay, so if you look at the equation at the bottom of this slide, here you can see that, just a minute. Okay, here you can see that when we take the limit, or sorry, when we take the value of this omega to be 0, we come back to the static case. So if you put here the value of omega to be 0, then you have here the second term sine 0 is 0, and here you have cos 0, which is 1. So in the bracket you have only 1 upon r, which is multiplied with 1 upon r outside, so you get 1 upon r square. So p0 cos theta by 4 pi epsilon 0 r square. This is the electric potential, value of the electric potential you get for the static case. This I think you must have derived in your 12th standard, because in that there is a problem of dipole field that you have to do. Now let us go ahead with this equation only. If we do not put omega is equal to 0, because in our case omega is not 0, we are considering atomic dipole fluctuation. So omega is having a very large value, because in atom, if you take the atomic dipole, its frequency is very high. Okay, so let us now move to the next slide. So in this second approximation, we took that only. Our omega is very high. Suppose you take the case of say blue light, then the value of it is its frequency is of the order of 7.5 to 10 raised to 14 hertz. Okay, so if you take the value of C, which is 10 raised to 8 meter, then this C by omega is a very small number compared to R. So R is much larger than C by omega. So if you put in this equation the value of C by omega or omega by C, suppose you invert it, then 1 upon R would be much smaller than omega by C. So here in these two terms, for the first term is having 1 upon R, the second term is having omega by C. So 1 upon R term is much smaller compared to the second term omega by C. So the first term would be neglected. So we have this term only, the second term. So we have the time varying electric potential of the nature of minus P0 omega by 4 pi epsilon 0 C into bracket cos theta by R into bracket sine omega t minus R by C. Okay, so this is the final equation of the time varying electric potential that we have derived. Now let us we shall see what does it imply, but first let us derive the time varying magnetic potential, vector potential. Now in order to derive time varying magnetic potential, we have to have some current first. Now how we can consider a current? Here the charges are in motion, so they constitute current. Now how can we represent current? I instantaneous, because this current would not be a steady current because it is made of a discrete charges, and that too are oscillating. So they are not moving with constant velocity, they are moving with varying velocity, and they are discrete charges. So we can say that the current which is produced by this oscillation of these charges would not constitute steady current, but it would constitute an alternating current or oscillating current. So this current, the instantaneous value of this current is given by this equation. I of t is equal to it is nothing but the dq by dt, and its direction is in the direction of z-axis. So we put the value of q, which is nothing but q0 cos omega t. So we have to take time derivation of q0 cos omega t, and when you differentiate q0 cos omega t with respect to time, we get minus q0 omega sin omega t, because cos omega t, the differentiation of cos omega t is minus sin omega t, and then we have to differentiate omega omega t also, so we get 1 omega outside. So, and the time that we have taken here is t prime, okay, retarded time. Here also we have to have the concept of retarded time, because here also the observer at point P, what it sees the value of current at time t is not the value of current which is there at time t inside this dipole, because this news of the current reaches after some time to point P. So the observer sees the current of some time back. So here also we have to put the concept of retarded time t prime. So now let us see, suppose in the slide in the figure which is given adjacent to the equations you see. So let us take one point of time and we have this current segment dz. Okay, now this current segment, suppose here you can see the current segment dz. Okay, now when as the charge moves, this current segment moves. Now the instantaneous distance from this current segment to the given point is given by this symbol of r. See, okay, this symbol is different than this symbol because this is the instantaneous value of r, the distance which changes with the motion of the current segment. Okay, and this distance, this is the symbol of the cursive r, and here is the symbol of r in the small letters. So this is the constant distance from the center of the dipole of the given point, and this is a time varying distance from the current segment. Okay, so now according to the definition of the magnetic vector potential, how we have defined magnetic vector potential? We have defined magnetic potential as this, yeah, as given in this equation, mu0 by 4 pi. Now we have to take integration because we have to take all the current segment into consideration. So we have to take integration over z axis, line integration, from minus d by 2 to plus d by 2. We have to consider all the current segments which contribute to the given point P. So we have to carry out this integration which is shown here. Okay, where this r is the instantaneous value of distance from the given current segment. Okay, now just a minute. So here, now let us put the value of this r, which is instantaneous distance. We have already worked out this value, which are shown here. This r can be represented as r minus d cos theta by 2, and 1 upon r we have derived as 1 upon r plus d cos theta by 2 r square. This r is the constant value, this r is instantaneous value. Okay, so we put this value at the place of the r which is in numerator part and r which is in the denominator. So here we put the value of 1 upon r and here we put the value of r. So let us take this term first. This term, we shall take this term first, and we put the value of this r, and which is nothing but r 1 upon c is as it is, minus 1 upon c. So minus r by c. Here also we have minus inside, and outside also we have minus. So plus 1 upon c would be carried inside. So d by c cos theta by 2. Okay, so this is the placement of value of instantaneous r. Okay, and then we shall put the value of 1 upon r also here. We shall put the value of 1 upon r from this equation. Okay, this equation we shall put. So it would be in multiplication with this term because it is the value of 1 upon r. So we shall now expand this particular. Okay, so here we have expanded it. Okay, now you can simplify it by taking the approximation. Here d is much smaller than c, and d is also much smaller than r. You know that d is the atomic distance. It is of the order of 1 angstrom, and the value of c is much higher. So d is much smaller than r and c. So if you put here the value of d, this term and this term both would be negligibly small, so you get this equation q0 omega sine omega t minus r by c into 1 upon r. Okay, so we put this value put for the integration. So here we have now this term r is, see, in the former integration, the instantaneous r we cannot take out because it is changing with the current segment. So if you start from the bottom end, and if you go on taking one after the other current segments, when you take the current segment, its instantaneous position also is changing. So instantaneous r is a variable of integration. We cannot take it out, but this r is not a variable of integration, so we can take it the whole term out. So here we have taken the term out, and we get only this value. Okay, at the place of t minus r by c, now we have put t prime again. Okay, and 1 upon r we have taken, so this whole term we have taken out. So what remains inside is only dz. So it is the integration of dz in the limits minus d by 2 to plus d by 2, and which comes out to be the value of distance between two, maximum distance between two charges, d. Okay, so here we have worked out this integration. Direction is still in the direction of z axis. So this is the value of the magnetic vector potential, which is measured at the point P by the observer. Okay, so two equations we have got. One is the time varying electric potential, which has the form what we had just seen, and this is the magnetic, scalar time varying electric scalar potential, and time varying magnetic vector potential. So this is time varying magnetic vector potential. Now our task is to work out the time varying electric field from these two terms. Okay, so how can we have, just a minute. Okay, so how can we work out the electric field, time varying electric and time varying magnetic field from these values of time varying electric and magnetic potentials? So electric potential, as you, this is also content of unit 1, I think, yes, unit 1 of this paper. So time varying electric field can be shown as minus gradient of V minus del A by del T. Okay, this is how we define electrodynamic field, which can come into effect by time varying electric and time varying magnetic potential. And magnetic field is shown by the curl of A. So these two equations we have. Now let us find out the value of E and B in this case. So first we shall take the value of gradient of V. We shall derive the value of gradient of V, and then we shall derive the value of del A by del T. Okay, so here let us first calculate the value of del A by del T. Okay, differentiation with respect to time of the magnetic vector potential. So magnetic vector potential we have derived, which is this. Okay, and let us take the differentiation with respect to T of this equation. Again, the differentiation of there are two variables. We have to take differentiation with respect to T. So the differentiation of sine is cos. So minus sign is as it is. Here we have cos omega t, and then we have to differentiate the term inside this bracket, and which comes out to be just omega. So here we have one omega was already there, another omega has come, so omega square, and so minus mu 0 p0 omega square by 4 pi r into cos omega t minus r by c. Uh, the direction is still is in the direction of z axis. Okay, so now we can put at the place of this unit vector z. Now we can show this by this equation. We can show this unit vector z as cos theta into unit vector r minus sin theta into unit vector theta. How? Let me show you this. You can understand it with this figure. See, let me again change it to the pointer. Okay, I'm changing it to the pointer again. Just a minute. Okay, so here, now you can see here. See, here we have this current segment moving in the vertical z direction. Okay, so at any point of time, we have this distance from the given position of the current segment at a given point of time. Now let us take this triangle. Now we are taking the displacement vector. Okay, there are two vectors. One is instantaneously varying vector r, and one is constant vector r from the center of the dipole. So we are taking the difference of these two vectors. Okay, because it is moving. This current segment is moving from this point to the next point. So we are taking the change of current with this duration of time. Okay, so what would be the value? What would the change in the magnetic vector potential because of this change in current in this infinitesimally small interval of time? So we have to take the difference of these two vectors. Okay, first the current segment was at this point, then after the current segment moved to this point, and in between there is a change in this value of a in this infinitesimal interval of time. So we take the difference of these two vectors. Now this is z, as you see. Now this is the direction of del by del t, the small change which is done in the value of a in direction z. So z, unit vector z, is this. Okay, this is unit vector z. Now if you take at this point, see, the direction of this vector is r. Now we are taking everything in spherical polar coordinates, so it has three coordinates. One is r and other is theta and phi. So theta is this, which is already shown. The angle this r, the displacement vector from the center of the dipole, it makes, okay, is given by this theta. Okay, so and the change in theta would be having this direction, tangential direction. Okay, so this is another coordinate of spherical polar coordinate system. This is r, radial coordinate. This is angular coordinate theta. So now let us see. So we have this geometry in which this angle is theta. So in this geometry, this angle is theta. This is theta between Z and R. Okay. Now, you take two components from this vector Z on R and theta. So this component would be minus theta sine theta because it is in the reverse direction of theta. So minus theta. Since this is value of theta, this component is sine theta. So minus theta into sine theta, and this component is cos theta because in the direction of r, so it is r cos theta. Okay, because this value is theta. Z and the angle between Z and R is theta. So this is theta, R cos theta. This component is R. So Z is made of two components, R cos theta and minus theta sine theta. So Z is equal to this cos theta R minus sine theta theta. So yeah, putting the value of the Z here. So okay, now we can work out the value of delta V or gradient of V. Okay, so now the gradient of V in spherical polar coordinate system is defined with this equation. Again, let me convert it into pointer, lesser pointer. Okay, so with this equation we represent the gradient of V in spherical polar coordinate system. Any vector, its gradient in spherical polar coordinate system is represented by this equation. Now you put the value of V in this equation. The value of V is this, that what we have derived. Okay, now we have to differentiate with respect to R. Now here you see at two places there are the term R comes here at the denominator place 1 upon R, and here inside this sine function we have this R. So we shall employ the chain rule to work out this differentiation. First we shall keep one term constant and we take the differentiation of the other term. So here we have taken this sine omega term constant, this R term constant, and we have taken the differentiation of 1 upon R. So the differentiation, this minus sign is as it is, this sign is as it is. Okay, and the differentiation of 1 upon R is nothing but minus 1 upon R square. So one more minus sign has come here. Okay, so this is the first thing. Then in chain rule we have to take the other term constant. So now we have to take 1 upon R constant and we have to differentiate this sine term. Okay, so differentiation of sine term is cos. Okay, 1 upon R we have taken constant. So 1 upon R into the differentiation of sine term, which is cos omega t minus R by C. Okay, then we have to differentiate the term inside. So we have to differentiate omega t minus R by C. So 1 omega will come here. Okay, 1 omega will come, and the differentiation of t is 0. So minus sign will come now, minus, and differentiation of R is 1. So minus omega by C. So this omega by C will come. Okay, so this is how we have differentiated this V with respect to R. Okay, and then let us differentiate this V with respect to theta to work out this second term. Okay, in this not a representation of gradient. So here we have to differentiate V with respect to theta. Now theta term is at only one place, cos theta. So everything else is constant, and we differentiate this cos theta with respect to theta. So minus sine theta would come. Okay, so we have these three terms. Now let us put them together in this equation. this gradient of V is equal to this first term is having these two terms, this expansion, and at the place of 1 upon R del V by del theta, we shall put the value of del V by del theta. Okay, so we have already multiplied this del V by del theta with 1 upon R. So here we have got 1 upon R square. Okay, so now we have put them together in this equation. Just as it is, we have put the values of first and second term. Now let us take the last approximation. Now this approximation tells that R is much greater than omega by C. Okay, R is, this is we know. So if R is much greater than omega by C, then if you take inverse of it, 1 upon R is much smaller than C by omega, and so 1 upon R square in comparison with C by omega would be negligibly small. So this 1 upon R square term we can neglect with respect to the other terms. So we get only this term. So 1 upon R square terms we are not taking. So we get this term only. Now let us put this value of gradient of V in the equation of electric field. So now we have worked out gradient of V as well as del A by del T. So now let us put them together. This first term is the value of gradient of V, and this second term is the value of del A by del T. So if you expand this bracket, and then here if you see, here we are having 1 upon C square. Here we are having 1 upon C square. Now you know from the third or the second unit, 1 upon C square is nothing but mu 0 into epsilon 0. Okay, because for free space the speed of light is equal to 1 upon under root mu 0 epsilon 0. So we shall put this value, just a moment, okay, so we shall put this value at the place of 1 upon C square. We shall put mu 0 epsilon 0. This epsilon 0 would be cancelled with the epsilon 0 in the denominator part. So we will have here only mu 0. Now when we put here mu 0 and cancel this C square, this term is exactly equal to this term. Okay, when we expand this bracket. So here we have cos omega t minus R by C into cos theta. This first, the this component of R, and here also we have cos omega t minus R by C into cos theta. Okay, here we have minus sign, here we have minus and minus, so plus, so these two will get cancelled. So what we actually get remaining is this term. Here we have minus sign which is multiplied, we have minus term, okay, which is multiplied with this minus, which is plus, and again it is multiplied with this minus, so we get minus term here, okay, minus sign here. So we get this term only, okay, the term with the sine theta, okay. So this is our, see, this is our electric field, time varying electric field that we have derived for this case of oscillating dipole. Now let us in the same manner calculate time varying magnetic field. Now how to calculate time varying magnetic field? We have to take the curl of A. Okay, curl of A we have to take. So A we know is given by this equation. Here we have to put the value of z. So this term in multiplication with cos theta r minus sin theta theta, and when we expand this term we get these two terms. Okay, this minus would be here, and when we expand it, this minus minus would become plus. Okay, so a is now represented by these two terms. Now how to take curl of a? The curl of a can be taken or can be calculated by this determinant, by taking the value of this determinant in the spherical polar coordinate system. We can here we have to put the value of spherical or polar coordinates r, theta and phi. Now at the place of in the second row we have to place the components of this del operator. In spherical polar coordinate system, it is 1 upon del by del r, 1 upon r into del by del theta, and 1 upon r sin theta into del by del phi. These are the components of del in spherical polar coordinate system. And at the place in the third row we have to put the component of a in 3 coordinates, r, theta and phi. So ar, a theta and a phi. Now let us put, now you know here we have to give 3 components, okay, of a, ar, a theta and a phi, but our function does not have dependence on phi, because if you inspect our function, it has only theta dependence and r dependence here. R is given, a is given by these 2 terms, but there is no phi in this equation. So our a has only r and theta dependence, not a dependence on phi. So here this component, when we take this first component r, we shall have to multiply these two, a phi into this 1 upon r del by del theta, okay, but a phi is 0, so it would be 0. And here we have to take a theta component and have differentiation with respect to phi. Again, there is no phi, so this differentiation would be 0. So r component would be 0. In the same manner, theta component would also be 0, because a phi is 0, and since there is no phi term, when we take differentiation with this respect to this phi is also 0. So r and theta component would be 0. Only phi component would be there, because here we have to take out phi component. We have to take out differentiation of a theta with respect to r, and we have to take differentiation of ar with respect to theta. So let us do that. So when you do this, okay, so here it is done. So this curl of a is limited to this term only. Okay, curl of a is just limited to this term. So let us take, here we have taken, see, when you multiply these two, del a theta by del r minus 1 upon r del ar by del theta. Now we are taking out 1 upon r, so we have to put r in multiplication with del a theta by del r. We are taking it inside. Here we are taking r because r is constant. So we are doing it this way. Okay. So how do we do this now? We have to put the value of a theta. So we have put the value of a theta here, value of a theta. Okay, so when it is multiplied with r, it has only mu 0 p 0 omega by 4 pi into this term. One r is here. Okay, so we have to take the differentiation of sine theta first, which is nothing but cos theta, minus cos theta, so minus sign would be there. Okay, and then we have to differentiate this term. which again would be, sorry, the differentiation of sine theta would be cos theta only, positive, and when we differentiate the term inside this bracket, there would be minus 1 upon c. So minus 1 upon c we are taking out here, and we have 1 omega would be coming when we differentiate this sine theta. So this omega would be multiplied here, so omega square, so get this term. So this is the first term. Now for the second term we have to differentiate AR with respect to theta. Now AR is this from this equation, the component of R, so it is given by this. Now we differentiate with respect to theta. So again there is only sine theta term having theta inside, so we have to differentiate sine theta. Okay, sorry, cos theta term is there only. Just 1 minute. Just a minute. Excuse me. Yes, sir. Ha 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 ha.
તો સાહેબ તમારું માઇક બંધ છે.
Okay, sir. Okay, so we shall continue with our work. We have started little late, so it will take little longer, but we shall try to complete this portion totally. Okay, so let me just 1 minute. So here we have worked out. So I will not go in much detail with this derivation because we have gone into very detail of it. But here you can see when you put this value, see up till now we have done. Here we have done. Now, okay. So when we actually so we are differentiating the R component with theta, and this is what we have done here. There was a minus sign here. See, minus sign here. Okay, this is not working. This mouse is staggering. Okay, okay, whatsoever. So there was one minus sign term. So when we took the differentiation of sine theta, we had one other minus. So here we have the plus term. Okay, now we put this value inside this bracket. So when we put this value inside this bracket, we get del cross A, which is represented by these two terms. Okay. Now we shall put this approximation again, what we did in the case of time varying electric potential also when we derive electric field. Here also we shall put this the same thing, and we just neglect the term having r square, 1 upon r square, so we get this value of magnetic field. Okay, so this is how we have derived electric time varying electric and magnetic field. So this was the mathematics only. Just you have to be careful while expanding the terms, and that's all. But now what specific about these two terms, that is very interesting to know. See, we have derived this electric time varying electric field and time varying magnetic field, and if you look at the nature of these two equations, see the nature of these two equations. In the next slide, you just see the nature of these two equations. Here, they represent this type of behavior. There is a change in the electric field component with a sinusoidal change of the electric field component, sinusoidal change of the magnetic field component. Electric field component is change in of electric field component is in the direction of theta. Change in the magnetic field component is in the direction of phi. So they are mutually perpendicular. Okay, so they are something like electromagnetic radiation in which two components are mutually perpendicular, oscillating with the same frequency. Now here you see one other noticeable thing is that it does not have 1 upon r square dependence. Okay, so if you had taken the Coulombian approach, the electric field that you would derive would have 1 upon r square dependence. If you take the Biot-Savart law, their magnetic field when you derive has 1 upon r square dependence. But here, strikingly, it does not have 1 upon r square dependence, but it has only 1 upon r dependence. See, so if I draw now, I want to show this field. I have prepared one animation for that in 3 dimensions. So I would like to show these two fields. We shall take only the magnetic field also because it is moving in phi direction. So just look at this animation. Here, this is z direction, this is r direction, and phi is the angle between this. This is theta direction. So this is phi direction. Angle, this vertical axis, and r. Angle between these two is phi. And angle between z and r, okay, between these two axes is theta. Okay, so what type of wave it represents? See, it represents this type of waves. These are the fluctuations of the magnetic field vectors, and it represents. This is the just what I have done is this equation. I have drawn this equation, okay, by the computer programming. So you can see here. See, it has first of all 1 upon r square, 1 upon r dependence. It does not see as these waves, as you go away and away from the center of the dipole, the amplitude decreases by 1 upon r. Amplitude is decreasing of this. Okay, and it has this sine theta dependence also. See, sine theta dependence. Now it is not, they are not emitting in all directions. They are emitted only in some specific direction. So it has now lost the property of omni this emittance. It is not emitted in all the directions. So this is the specific thing about these two types of fields, electric and time varying electric field and time varying magnetic field. Okay, so just 1 minute. Now let us calculate the whether these two fields, electric and magnetic fields, whether they constitute radiation or not. So for that what we have to do, we have to take the Poynting's vector. Okay, if you calculate Poynting vector and if it has 1 upon r square dependence, then we can say this energy which is leaking out has the form of a radiation. So we put the value of E and B in this Poynting vector. Again, this cross product is a simple multiplication only because the E and B are mutually perpendicular. So sine theta is sine 90, so 1. So if you put the value of E, what we have just derived, and the value of B. Now these two terms are the same, except B is much smaller. How much? 1 upon C times smaller than E. Okay, so we take out 1 upon C, and here we are having 1 upon mu 0. So we take out mu, this mu 0 into this mu 0. We are multiplying these two terms. So mu 0 square divided by mu 0 is mu 0 by C. So 1 upon C we are taking out, and mu 0 we have taken out. And we have the square of this term. These two terms are exactly as it is. Okay. And again, the direction is in the direction of R. Okay. So it constitutes the radiation. Why? Because now it has got 1 upon R square dependency here. Here you have the term 1 upon R square. So this is a form of radiation. This pointing vector shows the energy which is escaped from the given volume to the infinite distance. Okay, and which can be shown by this pointing vector, and in the form of radiation it radiates. Now you can have the average value of this. You can have the average value of this if you take the average, because this cost term, if you take average with one cycle, okay, of time, okay, then the cos square, if you take the integration of cos square with one period, it comes out to be 1/2. So if you take the average value per one cycle of the pointing vector, and it comes out to be this. So it has this sine square as well as 1 upon R square dependence. Now the former one was the electric field, okay, and magnetic field, which were having sine theta and 1 upon R dependence. Now the energy, now this pointing vector, this shows the average energy, and it has sine square theta and 1 upon R square theta dependence. So let me show you one animation for this also. Okay, so it is something like that. Suppose now you have a dipole at this point, particularly this point. Now how it emits out the energy? Now it is not emitting out the energy in all directions, but it emits out energy in this way. Okay, this is just the representation of the equation that we have just derived. Okay, this is sine square theta dependence, and 1 upon R square is not shown in this figure. I will show it in the next figure. So it is something like this. Suppose you look at it from the top, it has this type of emergence. These are, what are you seeing? You are seeing the energy values, okay, the changing value, or the time. Here they are in the form of values, but in equation we have taken the time average per one cycle of the energy. Okay, so these are, so this final animation now can see it in a more subtle way. See, this is the dipole. Now this is the, in Z direction we have this movement of dipole in Z direction, fluctuation of dipole, but I have not taken the physical fluctuation of dipole. I have just taken the fluctuation of the value of charge. Suppose you think of it as a surface of water, and there is a fluctuation of value of charge as some pebble which is moving up and down on the surface of water, then the energy which it creates in the form of waves is like this. So this is exactly how the energy is radiated. See here. Here you can see both the things, not only the sine square dependence. See, it is not omnidirectional. The emittance from this dipole is not omnidirectional. It is not in all directions. and as well as it has 1 upon r square dependency. These waves, as they go far away, they lose their amplitude by 1 upon r square. Okay, so this is the type of radiation that we get from a dipole, oscillating dipole. So these are what we have got. Now the example of this type of dipole is the atmospheric dipoles. Okay, these atmospheric dipoles, the atoms or charged particles, not let us not take the charged particle, that atoms in the upper atmosphere or atmosphere, when they come under the effect of sunlight, which is nothing but electromagnetic wave. So when they come under the effect of the electric time varying electric field of sunlight, they oscillate in the same manner as we have derived in this problem. So when they oscillate, they emit of the radiation. Now the radiation which they have absorbed in the form of sunlight, they will re-emit it, but they will re-emit in this manner. It will not, they will not re-emit this radiation in all the directions, but there would be a directional property. And one more thing you can see here, why we have got 1 upon r dependence. Suppose you have something having 1 upon r dependence, then it means that if 1 upon r raised to 3 or 1 upon r raised to 4 can be shown as some of the flux lines are terminating inside, then how can you explain 1 upon r dependence? Here it can be explained by this sine theta square emergence. See, formerly it were omnidirectional, having 1 upon r square dependence. In all the directions the waves were going, but now only in certain directions we have got all the energy coming out. So energy will not decrease with 1 upon r square, it will decrease by 1 upon r. So two things emerge together, sine theta dependence, sine square theta dependence, as well as 1 upon r square theta dependence. Okay. So I think if time permits, I can go in just completing this particular problem, why there is a blueness or redness of sky, and if you want to keep it up to this point only in this session, then let us conclude at this point. If you have any doubt, I am here to answer. Sir, over to the Vyas Sahib. Yes, sir.
પ્રશ્ન છે બાબુ.
Yes. Over to you, Vyas Sahib.
Okay, no problem.
I think because time is now running out, so we shall keep it at this point only. If there are some doubts, then let me answer. Otherwise, we can conclude this session at this point.
Okay, sir. We are.
મારો વાત સંભળાય છે?
Yes, સંભળાય છે સાહેબ. મારો વાત સંભળાય છે?
Yes, yes, sir.
Okay, so we want to keep here only, and okay, thank you very much, Jani Sahib. We want to limit up to this only. If time permit again and student want to listen you, we can take the feedback, and then on the feedback we can go for the another lecture also. And for the student point of view, you give your feedback in our group of lecture. A lecture for electrodynamics. Based on this, we can conduct it for 501 and 503. For 501, Dr. Gondalia Sahib and V.R. Rathod sir are already ready. And Arvind Aksan, Dr. Arvind Aksan from Christ College also want to take one lecture. If you are interested, we are providing the Google form, and then you fill the form. Based on this, we can conduct these lectures. For 503, Dr. Atul Patel from Kamani Science also ready to take the lecture, and other expert faculty from Jamnagar DKV and Rajkot Kotak Science also ready to take the lecture. But it all depend on your feedback. So I will send the feedback in lecture group. You can, or your HOD, you can fill the form, and if you want to continue this type of session, we can continue in the next week on same time 3 to 4. Thank you for participate. Once again, thank you all the faculty from different college who can cooperate to conduct this type of session. Thank you again, Jani sir, for give your valuable time for this two lecture. Thank you all the participate. We can end this session here. Thank you very much. We can meet again. Goodbye and good day.
Okay, sir.
Okay, sir.
Good day. Thank you.